speaker, Xiaoqin Zou. And that seems to be working. Okay, stage is yours.
So first, I would like to start with I would like to thank the CASP organizers for inviting me to give this talk. And also, I'm so happy that CASP is expanding and very inclusive. First, invite the Capri community to join the protein assembling prediction, and now this time for protein ligand and also and also RNA structure predictions. And also, I'm so happy to see Pat and Shiv for the assessors from D3R to continue to assess the quality, the structures here. So today's talk is about the title is template guided method for protein ligand complex structure prediction with application to CASP15. And the work is done by two young, highly talented scientists in my lab, Dr. Xianjin Xu and Dr. Ray Duan. And so first, I'll talk about the method we used for protein ligand complex structure prediction, and then how we apply it to CASP15 and the lessons we have learned from this study. So here's the general strategy of our template-guided method for predicting protein-ligand interactions. And the strategy is described in this paper published last year. So here's the flow chart with a query ligand. We will use omega from OpenEyes to generate up to 200 conformers based on the given SMILE string. And for each target protein, we will search in the protein data bank for homologous proteins that with cobond structures. And then we will use the shafts programmed by Liu, etc., to superimpose each conformer of the query ligand to the protein structure complex, the protein ligand structures. And then we will evaluate them and do the best superimposition. And we will also use orthodox Wiener to do local refinement and minimization. Then we will use our hybrid scoring function to rank them and then give the results. And this general strategy was developed based on the systematic analysis of this constructed protein ligand complex structural data set, so which is given here. And we built up this structural data set using the well-known proteins. Each protein has at least 70 cobond ligands, and they have 17 different proteins with a total of nearly 3,000 complex structures. The reason why we do this is because we want to understand the features of those templates. So by finding the correlation between the RMSD and the 3D similarity. So characterize the 3D similarity, we use the SHAPS program I mentioned before. And so for this SHAP score consists of two components. One is the shape score, so shows to compare the shape shape similarity, plus chemical score to compare the similarity in chemistry. 0 means no similarity, and 1 for each component means identical. So the maximum score for SHAPS is 2, which means the two molecules are identical. 0 means no similarity at all. And so we use this random cutoff, say 1.2. If the SHAPS score is above 1.2, we consider the two molecules to be very similar. And otherwise, they are dissimilar. And we also developed this 3D, this intercomparison strategy to do the superimposition. So, which is, I think people who work on protein ligand structure prediction knows that those superimposition is now trivial, particularly for for dissimilar ligands. So, so the details were described in the paper I mentioned before. Then, so this is the correlation. Of course, so without not unsurprisingly, when the Scheff score is high, so that means the two molecules are very similar. So the query ligand is very similar to the templates. Then the RMSD could be very low. So the lower the RMSD, the better the prediction. But that's not interesting. The interesting part is look at those two highly dense distributions. So one region is here. So this region, that's the Scheff score is about 1. So that means they are they are relatively dissimilar. And the RMSD is also high. So that means dissimilar template ligands bind in different ways. That's not surprising again. This is the interesting part. So here the RMSD, the Scheff score is around 1.1. So they are dissimilar ligands. However, RMSD is very low. It's below 2 angstrom. What does that mean? That means dissimilar ligands can also bind in similar ways in some cases. So that's something we want very interesting to us. So dissimilar ligands bind in similar fashion. And is that are those rare cases or not? The answer is no. This actually could be actually is kind of common in this database. So here, for example, the horizontal axis shows the criteria for RMSD for the what we so-called good prediction. So if we take, say, RMSD as 2 angstrom as a definition of good prediction, then you can see that for more than 95% of the cases, you can find at least 1 dissimilar templates that bind in a similar fashion. So basically, this figure shows that dissimilar ligands bind in similar fashion is not rare. And so here's the hybrid scoring function we use. It's composed of 2 components. One is the docking score. So in this case, we use AutoDock Wiener. So it's the Wiener score. And the other part is the Scheff score that characterizes the 3D similarity. And we introduce this coefficient to make the 2 scores comparable. So then we do the systematic docking, the systematic structure prediction. And so we use Wiener as the reference state. So the black curve shows the Wiener docking score. And we use the bound protein structure. That means the native protein structure. But the ligands is built from SMILE strings. And you can see that for RMSD of 2 angstrom, using that as the criteria for a successful prediction, the success rate for Wiener is about 45%. So this is the usual docking accuracy, the usual accuracy for docking. Then for similar templates, without surprise, the success rate can be as high as 85%. But for dissimilar templates, the success rate is about 65%. So it's still significantly higher than the docking bound accuracy. So here's what we apply this strategy to CASP15, and the protein structures were built based on the sequences using AlphaFold. And for the ligand 3D conformers, so the CASP provides us the SMILE strings. We build the conformers through 3D conformers using the OpenEye omega-2. And so we use 2 types of methods. One is the template guided method I mentioned before. And if there's no template, we'll just use AutoDock Wiener to do docking. And so to prepare for this talk, we have the following assessment. So we basically superimpose our predicted predicted structures with the experimental structures using UCSF Chimera and the matchmaker function. And we calculate the backbone RMSD of the protein targets. And also the most interesting thing, particularly for the predictions that are not too bad, we will also calculate the RMSD of the heavy atoms of the protein contact residues. So HRMSD stands for the heavy atoms, not only in the backbone, but also the side chain atoms of the protein contact residues. And then we also calculate the ligand RMSD, so the RMSD of the heavy atoms in the ligands. You see, and again, just as I think Dima also Pat and Dima mentioned, that it's not easy. So we use OpenEye's OEChem Python toolkit to do the superimposition, because the superimposition relies on the names of individual ligand atoms. So here, so we will I will summarize the results using different classifications. So these are if the targets have reliable templates, we can predict this the binding mode successfully. You can see that the H or heavy atom RMSD of the at the interface is pretty low, and also with low ligand RMSD. In some cases, even low quality protein structures still allow us to make reasonable predictions. So like this case, target 1124, for this part, so there's a big misalignment in the helical structures. So the backbone RMSD is 8.3, that's pretty high. However, we still get a reasonable ligand RMSD. The reason is because this ligand interacts with this part, with the part that's not misaligned. So that's why this misalignment wouldn't affect the structures. So one was using the template-based method. The other one is basically using docking, because there's no template at all. And in this case, I think Dima mentioned this one too. We also, so even though the protein structure is well predicted by AlphaFold, however, the RMSD ligand RMSD is not satisfactory. So you can see the binding site this part is almost correct. However, because there's a cofactor here, but that's not given in the CASP, mentioned in the CASP. So there's no, this cofactor was missing. And therefore, when we do the prediction, this tail, which is highly flexible, goes down. But in the crystal structure, because of this cofactor, so the tail moved up. So the big ligand RMSD came from this region, the highly flexible tail, where the cofactor blocks part of the binding site. Then the next question is how the conformation of the binding pocket is important. We don't actually, for protein ligand docking, the overall protein conformation is not that important, but the conformation of the binding pocket is very important. So this case is target 1158 is a membrane protein. There are two, so the CASP provides only one conformation, which is the closed state of this membrane protein. But we know that there are two conformations. This is an APC transporter. There are two conformations. So thank Professor Jianing Chen sitting in the audience. So his lab provides us the AlphaFold predicted structures for both closed form and the open form, because this case is a huge protein. So somehow we didn't have enough time to generate that. So Professor Jianing Chen gave that to us. So we use both and do the structure prediction, and we submitted both. So it turned out that even though one is closed conformation, the other is open conformation, the conformation, so one is in this cyan color, the other is in the magenta color. Both of them gave relatively okay structure, okay ligand conformation, ligands binding mode. The reason is because even though the big conformations is not correct, but the local binding pocket for these two different protein conformations are pretty similar. So basically it's the conformation of the binding pocket that's important for the ligand structure prediction. And so here, this case is a misleading template so we failed this case. It's the same protein, however, is for this ligand. So we found the template from here. And if you compare the CASP ligand, they look very similar. The Sheff score is as high as 1.3. However, there's a difference here. So the targeted ligand is charged, but the template ligand is not charged. So we use the template guided, which are here. So these three regions, but the experimental result is in the middle. So actually, I have this question for Dima, because Dima, maybe after this you can tell us, because you use multiple probes, right? 16 probes to find possible binding sites. So I'm wondering whether using your probes, you identify these three regions or not, because this is also another question for the CASP or the CASP organizers. Is it possible for this ligand to have multiple binding modes? Because we check these three binding sites. There are several positively charged residues there. So these three binding modes could be possible. So this is a question maybe we can discuss after the talk. And again, the flexible loops and flexible ligand would decrease the prediction accuracy. I think this one, Dima also mentioned this. I think we failed for the same reason. This is target 1181. No, sorry, this one, I mean, maybe, okay, this one is ours. So you can see that the ligand overlaps in most regions. Lower, from the alpha fold, there's this big so this loop, the conformation of this loop is not correct, and therefore so our ligand is pushed to the lower part, and therefore so this is from Dawkins, so that's how we failed due to the flexible loop and highly flexible ligand. This one was mentioned by Shen. So the structure prediction is almost right, but however, because of this side chain difference, the tryptophan 120, we didn't get it correct. However, if you look at this, the ring stacking is pretty good in the predicted binding modes. However, just in the experiment, it's also forming a ring stacking, but the conformation of the tryptophan are different. Therefore, we got not good enough prediction. Other cases, this case, 1187, AlphaFold gave the wrong structure prediction for the dimer interface, the experimental ligand falls to this region, the predicted dimer interface, but this should not be the dimer interface. So two things. First of all, that shows that indeed this region is good for interaction, but not for protein, is for the ligand. And secondly, this structure looks a little bit surprising, because you can see that this dimeric interface has a much smaller surface contact surface area than the predicted dimer from AlphaFold. And ions, so maybe I'll just mention this one. We predicted one out of three iron ions. However, the others we didn't do correctly. There are so many negative charges, so this is still a big challenge to us. Lessons. AlphaFold is very helpful, provides us the protein structure for protein ligand structure prediction. It is the conformation of the binding pocket including the sidechain conformation to guarantee the high accuracy protein ligand complex structure prediction. So templates can help, but also sometimes can be misleading. And challenging case issues, if the large conformational change, highly flexible ligands, and also if there are multiple ligands in the pocket, like cofactors, for example, and also for ion binding location, I think we still didn't, at least our lab didn't do a good enough job. That's all. Oh, sorry. Most important thing, thank people. So I want to thank the Dr. Shenjin Xu and also Dr. Ray Duan, and also for the protein interaction. So Dr. Li Min Chiu also did a great job. Also want to thank our long-term collaborator, Jianling. So in the past, before we have AlphaFold, we always use Jianling's structure for our predictions. Thank OpenAI and also thank NIH. That's all. Thank you.
Okay. Thank you very much for the presentation. In the interest of time, we should limit ourselves to one question, if there is.